This is example 3 from page 16 of the Strength and Materials course notes, where we're going to consider a beam that's supported at one end, so it's a cantilever beam, and we're going to draw the shear force diagram and the bending moment diagram of this beam. In the process of making these diagrams, we're going to consider the points at 1 meter here, so 1 meter from point A, and 2 meters from point A, as well as point A and the far end of the beam as well, which we'll call, as usual, point B. So let's start off by drawing a line to represent our shear force diagram here. So let's draw this across. This is a representation of our beam, and as such, we'll make sure we mark 0 for 0 shear force at either end. The left-hand end is our point A, and right-hand end is point B. So if we think about what's happening at each point along the beam, this gives us an idea of how we can draw this shear force diagram. So we start off at point A, and there's a upwards force of 9 kilonewtons being applied. So immediately we draw a line up from the left-hand end of our beam vertically. And this line is of size 9 kilonewtons, so we mark that on our diagram. We now want to think about what's happening at the first point, so the point at 1 meter away. So I should make a wee note here. Shear force at A is 9 kilonewtons. Let's consider the shear force at this point, 1 meter from the end of A. So we'll call it point C just to have a reference. So the shear force at C is equal to, we've got a force of 9 going up the way, but we've moved 1 meter along the beam. Now there's no point forces acting down the way. We do have a uniformly distributed load of 2 kilonewtons per meter. And since we've come along 1 meter of beam, that means we have a total downward force here of minus 2 times 1. So this means that the shear force at point C is 7 kilonewtons. And so we mark this on our diagram here, like so. Now, when we have uniformly distributed load and no point forces being added at this point, it's a linear slope, which means a straight line from where we were at A, sloping down to point C there. Now let's consider another meter along the beam, the shear force at point D. Well, we still have our 9 kilonewton upward force at point A, but now we have 2 meters of beam at 2 kilonewtons per meter, so it's minus 2 times 2. So we're left with 5 kilonewtons of shear force remaining. And so we plot this at point D on our beam as well. And this continues our straight slope down to this point. We mark 5 kilonewtons to indicate the value of the shear force. Then at the far end of our beam, the shear force at B, because we've got a point force being added here, we know that there's going to be a shear force just before we arrive at the point, and then we take into account that 3 kilonewton force. So what we do is look at the shear force total just before we get to B. So we say shear force just left of B. So that's everything before we add that 3 kilonewton force. So that's our 9 kilonewtons up. Now we've got minus 2 kilonewtons per meter over 3 meters. So that's minus 6 in total. So we're left with 3 kilonewtons to start with. And when we get to B, we're at 3 kilonewtons. Just offset at the end of the line. And then we consider the shear force just right of B, sorry. And that's where we add that 3 kilonewton force, or rather we subtract it because it's heading down the way. So the shear force just right of B is everything that's to the left of it. So 9 minus the 2 times 3, and then we've got a 3 kilonewton force acting down the way. So we subtract 3, and of course that leaves us with 0, as we'd expect. So 0 kilonewtons there. So I'll join up the rest of our line. We've got a straight line continuing down 3 kilonewtons, and then we have that vertical drop, which occurs at any point we have a downward point force being added. So that's what our shear force diagram is going to look like for this cantilever beam with a UDL across it and a point load added at the right hand side of the beam. Now we want to now do the bending moment diagram for this beam, and it's a similar approach. We work from left to right. Now often when we have beams in this course, we start off by writing down the bending moment in A and B are 0. This is not the case in a beam supported at one end. In fact, we're told in the question, or the circle in green, we're told in the question that a moment is applied, and it has to be because it's only supported at one end. So that means when we come to work out our bending moment, so I'll do our first one here, MA is equal to minus 18 kilonewton meters. And it's minus because that moment that's pictured in the question is anti-clockwise. So it's important to take that into account, and that will be part of every bending moment as we move along the beam. So we'll start off each bending moment with minus 18. Let's consider now the bending moment at point C. Well, we have MC is equal to, well, minus 18 to start with. We're going to have plus 9 times 1 due to the shear force being applied at point A, which is going to be a clockwise turning effect. And then we need to take into account the effect of the UDL in between points A and C. So if we remember, UDL is acting down the way, that's going to be a counterclockwise turning effect. The total amount of force will be equal to 2 times 1, 2 kilonewtons per meter over 1 meter of beam. And we always take the average position the force applies at, so it's halfway between C and A, and half of 1 meter is 0.5 meters. So what we're saying, I'll draw it in blue here, is effectively we're modelling this UDL as a 2 times 1 kilonewton force applying halfway along that 1 meter line. So that's how we find the bending moment at point C. And when we calculate all of that, that gives us minus 10 kilonewton meters. For MD, it's going to be something that's quite similar. I'll just erase that marker in blue there. So we start off as before, the minus 18 kilonewton meters from the support. We add the effect of the upwards 9 kilonewton force at point A. And of course, the distance from B to A is 2 meters, so that's 9 times 2. And we then take into account the UDL's contribution to the bending moment of D. So now we've got 2 meters of beam, so the total force in this section from A to D is 2 times 2. And the effective point it's applying at is halfway between A and D, so 1 meter along. It just so happens it's at point C, but it would be half of whatever that distance was. So that's times 1. If we put all those numbers into our calculator, we'll have minus 4 kilonewton meters. And lastly, we'll work out the bending moment at point B. Now, this is something that should be 0 in a cantilever beam that's supported at one end. The end that is supported, point A, should have a maximum bending moment. The end that's not supported, point B, should have 0 bending moment, and that should always happen. In assessment question, you could just write this down. However, since the example shows that we want to convince ourselves of this fact, we'll continue to write this out. So we have minus 18 plus 9 times 3 this time, because that force of 9 kilonewtons acting up in the clockwise turning effect is 3 meters. It's a full other end of the beam. And then we've got the effect of the UDL. So now the 2 kilonewton per meter force is multiplied by 3 meters of beam. And effectively, the average point we're applying at is halfway along that 3 meters, so it's times 1.5. And all going well, you pop this into your calculator, it will in fact come to 0 kilonewton meters. So the last part we'd have to do in this example is to plot this on the bending moment diagram. So once again, I'll draw a line representing the beam and 0 bending moment. And we plot all of these points, starting from the left. Now, if we remember the convention, when we have negative bending moment, we plot it above the line. So rather than plotting it below the line, we start off up here, negative 18 kilonewton meters above the line. At point C, we had got to minus 10 kilonewton meters. At point D, we got to minus 4 kilonewton meters. And of course, at the end, we got to 0. So this point is slightly lower down because I made my graph a bit out of shape here. That's a bit more like it for point C. Now, what we should have, because if we go back and look at our shear force diagram, because we have a slope for our shear force diagram, it's a straight line slope, it's a slope. That means what we're going to have is we initially rise up from 0 to 18, and then we're going to have a curved slope. This is not a straight line. It might look a bit like one of my straight lines. It's a curved slope all the way down to 0. So maybe that point 4 should be a bit lower there. And that's the value of doing a scale diagram, is that you won't have these difficulties in sketching. There'll be a curved graph starting 18, going to 0, the high point at the left-hand supported end, the 0 at the right-hand free end of the beam. And that's how we find out the shear forces and bending moments and create these two diagrams for a question of this type.